Welcome back. In this video, we will discuss some examples of solving one-dimensional motion problems using kinematic equations. A jogger runs down a straight stretch of road with an average velocity of 4 meters per second for 2 minutes. What is his final position, taking his initial position to be 0? So when you do these kind of problems, we have to follow several steps. So the first step is drawing a diagram for the situation. And that helps you to imagine what's going on and understand what kind of motion you are dealing with. The second step is writing down known and unknown variables. The third step is picking up the correct equation that is suitable for your problem. And then the final step is solving the problem. So the joggers start running from the initial position, let's say x naught, and then run for 2 minutes and come to the next position that we don't know. Now we have to write down known and unknown variables. So the known variables are the average velocity is 4 meters per second, time is 2 minutes, and that's all the information given. So the 2 minutes, we will have to convert this to seconds. So this is 2 times 60 seconds. So that is 120 seconds. And now we have to decide which equation that we want to use. So from our list, we can use the first equation, which is x equals x naught plus average velocity times t. Now x naught, we can consider that as 0, and the average velocity is 4 meters per second multiplied by 120 seconds, we get 480 meters. So you can see here this seconds cancels out with this second, leaving us with the final answer in meters. So the x position at 2 minutes is 480 meters. Let's look at another example. An airplane lands with an initial velocity of 70 meters per second and then decelerates at 1.5 meters per second squared for 40 seconds. What is its final velocity? So let's start this problem by writing down the known and unknown variables. So known variables is initial velocity v naught is equals to 70 meters per second, and acceleration is given. It says it's deceleration, so this will be negative 1.5 meters per second square, and then time is given as 40 seconds, and that's all the known variables, and we have to find the final velocity. So when you look at these known variables, we can figure out which equation to use from our list. So if you look at the list of equations, we can see that the third equation, V equals V naught plus AT, is going to work well because we know this value, we know this value, and we also know this one. So we can directly use this equation to this problem. So this is going to be 70 meters per second plus and then negative 1.5 meters per second square times t is 40 seconds. And we get 10 meters per second. Let's look at another example. On dry concrete, a car can decelerate at a rate of 7 meters per second square, whereas on wet concrete it can decelerate at only 5 meters per second square. Find the distance necessary to stop a moving car at 30 meters per second on dry concrete and on wet concrete. Let's draw a rough diagram for this problem. The initial velocity is 30 meters per second, and then the car applies brakes and come to a complete stop. So we final the final velocity is 0 meters per second, and we have to find what is the displacement. Now we have to work with two different scenarios. In the first one, the braking is happen on dry concrete, so the acceleration is negative 7 meters per second square. On wet concrete, the acceleration is negative 5 meters per second square. Now in this problem, we know the initial velocity, we know the final velocity, and we know the acceleration, but we do not know the time. And we do not have to find the time because the question do not ask about it. Now if we look at our equation list, we can find out which equation to use. So if you notice, the fifth equation do not have time involved, and it has initial velocity, final velocity, and acceleration and change in position. So that equation suits well for our problem. So let's pick that one. So v square equals v naught square plus 2a x minus x naught. Here this x minus x naught is equals to delta x. So we can rearrange this equation to find what is delta x. So what we can do, we can bring this v naught square to the other side of the equation. So we get v square minus v naught square equals 2a delta x. And then we can divide both sides by 2a. We find delta x is equals to v square minus v naught square divided by 2a. Now we can use this equation for both of our situations. So if we look at part A, in dry concrete, delta x is equals to final velocity is 0, initial velocity is 30 meters per second, and then this divided by 2 times the acceleration is negative 7 meters per second square. So the final answer here is 64.3 meters. And for part B, we can use the same equation. So delta x is equals to, again, the final velocity is 0. Initial velocity is again the same, 30 meters per second. So this is squared divided by 2 times negative 5 meters per second square, and this is equals to 90 meters. These examples show that equation choice depends on which variables are given. So the best thing to do is first you write down all the given known variables, and then you look at the kinematic equations to figure out which one best fit our question and which equation make it easier for us to solve the problem. So if there's only one unknown variable in the equation, then we can pick that equation because it's easier to find the answer from that.